In our previous lecture, what we treated was how to get the shortest distance between 2 points and how to minimize the time taken for an object to fall from any height to the ground. But in this question, we are being told to maximize the area, that is, find the equation of the curve that maximizes the area. In this case, the other one was minimum. This time around, if you want to maximize anything, what you apply is what we call the Lagrangian multiplier. But for you to be able to maximize anything, the first thing you should be able to understand is what type of geometry are you maximizing? Are you maximizing a point? Are you maximizing a line? You can maximize a point to generate what is called a circle. You can maximize a point to generate what is called a cylinder, a sphere. But in this case, you have the area and you have the length. Automatically, the length is far bigger than the length. So what you need to maximize in this case is the length in order for it to cover the entire area. So the first thing you have to do is to generate what is called the Lagrangian equation. You are able to generate the Lagrangian equation, that is, you represent it as h, which is equal to a plus the Lagrangian multiplier plus L, where this is the multiplier. Once you are able to establish this equation, then the problem is solved. Then the next thing you have to apply now is now the Lagrangian equation, which is partial h, partial. You have to look at all the values, all the variables in the equation. If you have x, it will be equal to partial h, partial x minus d dt into partial h, partial x prime is equal to 0. From this equation, we can also know that by taking this one to the other side, automatically our partial h, partial x is equal to d dt into partial h, partial x prime. Once you are able to solve this, then it means the problem is solved. So now let's now apply what we've actually taught to the problem on the chalkboard. The question goes thus: the area of a domain bounded between points A and B. We don't know the kind of shape it is. We don't know if it is a circle, if it is a sphere, if it is a cylinder, if it is a rectangle, whatsoever. By x of t, that is, x depends on time and y also depends on time, is given by A, this is the area, where x prime is the x dt, y prime is the y dt. If the length of the line from point A and B is L, is a constant, and the length is being expressed as this, find the equation of the curve that maximizes the area. Automatically, you can decide to use another notation other than h, but in order to follow the norm, we can use h. But in this case, note that h does not represent the Hamiltonian. H is not the Hamiltonian. You can use f as well. So automatically, what you are going to have is, for this case, you can decide to use h is equal to a plus the Lagrangian multiplier, then L. This is the established equation. Let's call it equation 1. So what is h? H is equal to what is a? A is what is in the bracket without including this integral sign. So we are going to have 1 over 2 into bracket x y prime minus x prime y plus the Lagrangian multiplier. Then what is L? You only pick this without including the integration sign. So you have square root of x prime squared plus y prime squared. So we now apply the Lagrangian equation by saying our partial of h, partial of x is equal to d dt into partial h partial x prime. So what is partial h partial x? You now go to the expression. Where do you have x? You only have x here. There is no x here. So if you differentiate this one, this one is 0 because it does not contain x. It contains x prime, not x. So if you differentiate this, you are going to have y prime over 2. So we are done with that. So what is partial h partial x prime? If you look at this place closely, we have x prime here. Automatically, this one is a constant since it does not contain x prime. So this place you differentiate it. So that will give us minus y over 2. So we have minus y over 2. This place also contains x prime. We can either differentiate it directly or we use the function of a function to differentiate it. If you want to differentiate it, because this expression, this particular expression can be written as, let me just assume it is y, but let me don't use y, let me assume it is m. M is equal to lambda into x this plus y this against 1 over 2. So it can be written like this. So if you want to differentiate this, automatically this half will be the first to drop, which will be lambda over 2. Then the next thing, we differentiate this, which is 2x prime into x prime squared plus y prime squared against 1 over 2. So that is differentiation. Or we use the function of a function. But if we don't want to use the function of a function, we can differentiate it directly, which is this. So we introduce this to the equation above. So we have plus lambda over 2, 2x prime into bracket x prime squared plus y prime squared 1 over 2. So this one will eventually become, this will cancel this. So automatically we are going to have minus y over 2 plus lambda x prime. Because of this half, so we are going to have 1 over square root of x prime squared plus y prime squared. Then the next thing is, what is d dt of this partial h partial x prime? Automatically it will be d dt into the bracket of this plus lambda x prime against square root of x prime squared plus y prime squared. So what is the differentiation of y? It is still the same as y prime against 2 plus, just bring this into this, you are going to have d dt into lambda x prime against square root of x prime squared plus y prime squared. So let's leave this like this without differentiating. So we have to return our solution into this equation, into the Lagrangian equation, that is partial of h partial of x is equal to d dt into partial of h partial of x prime. So what is this? This one is being represented by this, which is y prime over 2 is equal to, what is this entire expression? Minus y prime over 2 plus d dt into lambda x prime against square root of x prime squared plus y prime squared. So by the time we transfer this from this side to the other side, we are going to have y prime over 2 plus y prime over 2 is equal to d dt so automatically, what is the, by the time we add them together, we are only going to have y prime is equal to d dt into lambda x prime against square root of y prime squared plus x prime squared x prime squared. So what is y prime? It has been defined here that our y prime is dy dt. We are going to have dy dt is equal to d dt into lambda x prime against square root of x prime squared plus y prime squared. So automatically, since dt is common to both sides, we can cancel out dt. Since there's dy against d whatever, we can introduce integration to both sides. By the time we integrate both sides, this is what you are going to have. Dy is equal to the lambda x prime against square root of x prime squared plus y prime squared. By the time we integrate this, what we are going to have will just be equal to y is equal to lambda x prime against square root of x prime squared plus y prime squared plus y naught, which is the constant of integration. So by the time we transfer this to this other side, what are we going to have? We are going to have y minus y prime is equal to lambda x prime against square root of x prime squared plus y prime squared. Let's assume that is equation 2. Let's label it as equation 2. So we are done with y. So we are done with x, which is variable x. Which other variable exists in this particular expression? So we have to solve for y too. We have to solve for all the variables that are present. So let's now solve for y. Using the same Lagrangian equation, which is partial of this, partial of y is equal to d dt into partial of h, partial of y prime. Let's label it as equation star star. So what is partial of h, partial of y? From this expression, there is no y here, so it means this is a constant, but there is y here. So by the time we differentiate this, we are going to have minus y prime against 2. So this one is going to give us minus x prime over 2. So what about, and in the other side, on the other side there is no y, there's only y prime here. So what is partial of h, partial of y prime? So from here we have y prime, here we have y prime. So by the time we differentiate this, we are going to have x over 2. So we have x over 2. Here, this place doesn't contain y prime, so this one is assumed to be a constant. So here, we actually apply the same principle with the way we actually solved the first one to differentiate this. We are going to have plus lambda over 2 into 2y prime into bracket x prime squared plus y prime squared 1 over 2. So this one is going to finally give us x over 2 plus lambda y prime against square root of x prime squared plus y prime squared. So now we have to now substitute this one and this into equation star star. So what is partial h, partial y? We have this. We have minus x prime over 2 is equal to, another thing, the next thing that I was supposed to do is to find the d dt of this particular expression. So what is d dt of partial h, partial y prime, which is equal to d dt into x over 2 plus lambda y prime against square root of x prime squared plus y prime squared. So by the time we differentiate, we are going to have, that is, d dt into partial h, partial y prime will be equal to x prime against 2 plus d dt into lambda y prime against square root of x prime squared plus y prime squared. So we have to substitute everything into this equation. So what is this from what we've gotten above? That is minus x prime over 2 is equal to x prime over 2 plus d dt into lambda y prime against square root of x prime squared plus y prime squared. So that's what we have. So by the time we bring this to the other side, we're going to have minus x prime over 2 minus x prime over 2, which is equal to d dt into bracket lambda y prime against square root of x prime squared plus y prime squared. So the next thing is for us to add. By the time we add, we are going to have minus x prime, which is equal to d dt into lambda y prime against square root of x prime squared plus y prime squared. What is x prime? X prime is the x dt. So we are going to have minus the x dt is equal to d dt into lambda y prime against square root of x prime squared plus y prime squared. Automatically dt can cancel dt. So our dx can also be represented as, by the time you multiply this negative to both sides, you multiply negative to both sides, so automatically negative will come to this side. We can also be written as minus lambda y prime against square root of x prime squared plus y prime squared. So on integrating both sides, we are going to have x is equal to minus lambda y prime against square root of x prime squared plus y prime squared plus x naught, which is the constant of integration. So let's bring the constant of integration to the left hand side. So we are going to have x minus x naught is equal to minus lambda y prime against square root of x prime squared plus y prime squared. Let's label this as equation 3. So we have equation 1, equation 2, and equation 3. So let me bring equation 2 forward. That is y minus y naught is equal to lambda x prime against square root of x prime squared plus y prime squared. That's equation 2. Let's square both sides of equation 3 and equation 2. By the time we square this and we square this, what we are going to have is x minus x naught squared is equal to lambda squared x prime squared against x prime squared plus y prime squared. Do you agree with this? By the time we square this, we are going to have lambda, the negative is gone. Lambda squared, oh, sorry, okay, this one is supposed to be, okay, this is correct. Then this one is supposed to be y prime squared. So we have y prime squared, then the square root is already gone, so no more square root. So let's label this as equation 4. What about equation 2? Let's square both sides of equation 2 also. By the time we square both sides of equation 2, so what we are going to have will be y minus y naught all squared is equal to lambda squared x prime squared against x prime squared plus y prime squared. Let's label it equation 5. So let's add equation 4 and equation 5 together. So after adding them together, this is what we are going to get. We are going to get y minus y naught squared plus x minus x naught squared is equal to lambda squared y prime squared against x prime squared plus y prime squared plus lambda squared x prime squared against square root of no more square root, x prime squared plus y prime squared. The LCM is x prime squared plus y prime squared. By the time this one goes into this one, we are going to have one, which is lambda squared y prime squared plus lambda squared x prime squared, which is the same as lambda squared into y prime squared plus x prime squared against x prime squared plus y prime squared. By the time you rearrange this one, we are going to have lambda squared into bracket x prime squared plus y prime squared x prime squared plus y prime squared. X prime squared plus y prime squared is the same thing as this, so automatically this one gives 1. So we are going to have y minus y naught all squared plus x minus x naught squared is equal to lambda squared. What type of equation is this? That is the equation of the circle. That is the equation of the circle. And the equation of the circle states that y squared plus x squared is equal to r squared. But from this particular equation, we can deduce. So let's label this as equation 6. Automatically, equation 6 represents the equation of a circle which has its centers at x naught, y naught, with radius what? Radius lambda. So what is